So, welcome everyone. First of all, I would like to thank the NoCook team for giving me this opportunity to speak. Um, NoCook and the work that it does is also a passion of mine. Learning, teaching others is definitely something that I love to do. And NoCook is a channel through which we can reach the Oracle user community in the Bay Area. And NoCook has been around a long time. I think most of us who have been in NoCook for a while will understand and know that this has been one of the most resilient and most knowledgeable of groups in the Oracle user community. So kudos to the NoCook team. With that, let me start. My name is John Kanagaraj. I'll introduce a little bit more about myself in just a second. But the topic today that we're talking about is how we scale databases at the database layer at PayPal. So let me get into this. This is the agenda. Will briefly introduce myself, the problems that we're going to talk about, and we'll get into the tenets of the problem, the basic things that we need to take care of. And from there, we'll take some deep dives into keys, the types of tables, the access path, database engines, and why we think about the way we think about data here at PayPal. Okay. With that, a little bit about myself. Many of you know me, but if you don't know me, this is a brief introduction to who I am, what I do. I'm currently a database architect at PayPal. I've been at PayPal almost 10 years now. It's been one of the most exciting phases of my career, which I've been at this for quite a while, 3+ decades, starting out with using one of the basic Unix, the SCO Unix, and Oracle 5.1. 5.1.16 to be precise. So it's been a long time. I've been using SQL, Oracle, and many other databases, as well as NoSQL and big data technologies in the past 6 years. Here at PayPal, we design and operate high-scale systems. Some of my colleagues today are going to be talking about some of those systems in the coming sessions, and I hope you stay around and listen to them as well. But on the community side, I've been a technical editor, an author. I'm an alumni of the Oracle ACE program, and I frequently speak at NoCook, Oracle user conferences, and so on. And as I said before, I love to mentor new speakers and authors. If you have a passion to write about technology, and especially about Oracle, I can help in terms of editing, showing you the right directions, and so on and so forth. So please find me on LinkedIn. My name is John Kanagaraj again, and I'd be glad to help you. So with that, what are the data platforms? What exactly are data platforms, and what are the characteristics of each of these data platforms that we need to think about? Again, this is something specific to PayPal, and the situation may be different in your organization. But generally, we would have system of record and some backend analytical systems, right? And the database team, database admin, database architects would be able to, are asked or tasked, responsible to manage all of them in the right way, right? So here at PayPal, we have the OLTP side of the house, which is the system of record. This is where we need to kind of create high-scale systems. But this data doesn't sit here because it needs to be analyzed, processed, and reported on. So we send this into something called the authoritative data source, or ADS layer, as we call it, with strict process integrity. And then this is taken to other data marts for reporting, analytics, and so on and so forth, right? We use different technologies here, database, data store technologies here. We'll talk about that in just a second. But the team that I work on is called the Site Data Architecture team. And this is where we play. Most of the work that I do is in the site and transactional databases. And we ensure that this data that is generated, massive amounts of data that is generated out on site, is sent into the authoritative data source databases for distribution then to other backend systems, Teradata, Hadoop, and lately BigQuery, right? So the characteristics that we need to have when we design these systems are what I'm going to be talking about today, because that requires a different way of thinking, right? So a lot of this is based on core tenets. These are the foundational tenets on which we build these systems. We'll talk about that in just a second, right? But before we go in there, what is the scale at PayPal, right? At the end of the day, all that we do supports a very, very large multi-billion-dollar business, right? In this slide, we talk about a lot of things. We have almost 400 active accounts now. This is in Q1. So in Q2, we've kind of touched 400 million. This is always increasing, and the pandemic has forced a lot of purchases online. Things which would have been bought in the store now is done online, right? So that has increased the pressure on our systems. It's a good thing for us, right? But the result of that on the database team is that we are asked to do a lot more with pretty much the same infrastructure or pretty much the same kind of architecture. And how do we manage this? That is the big question. So total payment volume on Q1 was $285 billion, which means that $285 billion of trade passed through our systems just in Q1. And if you kind of look at the trailing 12-month basis, this payment volume is more than $1 trillion. That is sometimes the GDP of a very, very large country in some cases, right? So when we are doing this higher volume, the responsibility on us is large. The scale requirements on this is large. The availability requirements are pretty large, right? So this is just to show the scale at which we do things. So what are these core tenets? The core tenets is that security is our number one, right? I know this is kind of in the background, but anything that we do this with security in mind. There are a strict set of standards we follow for securing our databases, securing our applications, securing our network, securing our people, securing the access to these databases, right? So that is the basic tenet. That's like, it's so much ingrained and part of us that sometimes we don't even have to think about it, right? But from a data perspective, this is what we manage, right? The resiliency, scalability, and the cost of ownership. So what does that mean? You must have heard this. Okay, we are up 99.99% or 99.9%, right? What does it really mean? So when we say that we want to be available at 99.999% available, we call this 5 nines of availability. It means that we can get a downtime of 5.5 minutes per year, 5.5 minutes per year across the entirety of our database organization, right? This is a very, very hard number to achieve. And we are able to achieve that with a lot of hard work, but then we'll look at what and how we do this, right? On the scale side, we talked in the previous slide about the scale at which we do things. right? How do we manage all of this at the database layer? Because all of this needs to land in the database. So we use distributed data stores, and that is something that we will talk about in this talk. Finally, we've got to keep count of all the dollars that we spend for all this infrastructure, right? How do we make it efficient? Because at the end of the day, you have to invest some to get some. Invest less to get more is the objective, right? And that is true for any business. You need to keep account of the cost of ownership, and we got to make it, whatever we do, much more efficient. So we'll cover all of these three. This is basically, looking at the tip of the iceberg. There's a lot of work underneath, which my colleagues will talk about in some detail later on. So what are the challenges at scale? So we found that we are pushing the limits on pretty much everything when it comes to Oracle databases or databases or network or anything, any physical infrastructure component which supports the business, right? So if you look specifically at Oracle, we are pushing the limits on connections. We have tens of thousands of connections to the database. So there is a limit on the memory, right? So each connection takes up memory. We have to provide space for the SGA, the PGA, the connections, and so on. So that has some limitations. Interconnect between in the large rack systems, we ran into interconnect limits. CPU, obviously. DDL on busy tables. So if there are tables that are accessed all the time, Oracle needs a DDL lock to make changes to those tables, right? And in a dynamic environment, we are changing a lot of table definitions, and that causes a problem by itself. Rack reconfiguration, when we need to patch or when a node goes down, the rack has some control mechanisms in the SGA to control access to the blocks. You know about the owner, the requester, and the holder of the rack blocks. All of that needs to be reconfigured when a node goes down. That can cause a significant outage. We started out with, I believe, a minute or 2 minutes per node. We worked with Oracle, the kernel folks and the rack folks to bring it down to 20 seconds. So redo rate. When we are making a lot of changes to the tables, the redo is pushed to its limit. IO latency, SAN, replication latencies, HA record, all of this is placing a lot of stress on the system, right? So what is our answer? So we came up with some solutions, and these solutions are very PayPal specific, right? We have talked about things like OCC, the Oracle Connection Cache, in previous NOCU presentations. We have used replication scale out to RO copies to provide read scale out. We have segmented, we've used microservice oriented architecture to provide logical separation so that we can logically separate out portions of our databases into separate databases. We have custom highly available cache, used to be called Mayfly, now we call it Juno, custom sharding, in which we'll talk about, and a lot of other things, right? Ultimately, we also want to move to the cloud, so we need to make all of this cloud ready. And this is a continuous journey. We're always pushing the limits. We are always innovating. We are always finding new solutions to problems, right? Just keeping maybe a few steps ahead of the problem itself. All right. So where did we start with? As with anybody else, it started as a monolith, a large single database, and the data layer was in this monolith database, right? So that is an anti-pattern, and we would never been able to scale with this process. So what was our first step? Our first step was doing some vertical database splits. So we went to a microservice architecture with which we could bound the activities of a microservice so that it's domain bounded. And then based on that domain, we could take the database, the monolith database, and split it into multiple domains, right? So each domain gets its own database. So we're kind of doing some horizontal splits, a vertical DB split. So just moving out into different domains. That held us for a while, right? But we came to a place maybe 6 or 7 years ago where we had to adopt sharding. So we took one of our main user databases and we created what is called shards. A shard is one part of the whole database. So we align, and we'll talk about this in a subsequent slide, but we take this workload and break it up into smaller and smaller pieces, right? And we call them shards. So that's the horizontal database splits. We also added read-only replicas because a lot of our activities are read-oriented, right? And it makes sense to provide read replicas. But the moment you have a read replica, what we found was that there is a replication delay between the live and the replica. And we had to introduce a cache in between to bridge this divide between the live database and the read-only replicas. Now, when we do all of this, obviously there is an effect in the application layer where we had to, as I said before, we go through this microservice architecture. We have to convert a lot of things. We used to be in C++, we went to Java, then adopted the microservice architecture. And when we did that, we could do the domains. But when it came to sharding, we had to really think about how this would be done. Because sharding introduces a lot more complexity in the data model. It simplifies it, but at the same time, it creates a lot of complexity in terms of how we manage sharding, how we manage secondary keys, and so on. So if you're interested, go back a year from today. I spoke on Noku on exactly the same topic as to how we shard databases. Okay. So there are a lot of things that not only at the database layer that we did, we had to do a lot of work in the application layer. And here is where, you know, the complexities comes in, the time comes in, the amount of effort comes in. Yes, splitting databases, I won't say it's not easy, it is difficult, but the complexity is more out here in the applications. And even as we did this, we had a lot of observations as we went along. Cutovers and failovers sometimes are the only time we know how much the blast radius is. We also found that when we split this by domains, there are some domain dependencies between various tiers, which caused problems, right? So maybe a tier 2 database going down, a domain database going down, affected the other domain databases. So ultimately, it decreased our availability. So these are problems that we kind of continue to encounter. So we came up with what we call a resiliency vision, right? I did mention something about the OCCs before. The OCC front ends everything, all the access to our databases. And with the OCCs, which we have now open sourced, you can make use of the same kind of technologies that we use here. We are able to come up with this 3 database pattern. One is the active, one is the local DR, where we operate local DR at the primary site. But we also have a DR database in another physically distinct site. Now this pattern, although we currently on site, this can go to the cloud, right? And it can go to the cloud because we can just take this and shard across multiple individual set of boxes, right? The cloud presents a different set of problems. It uses virtual machines. You do not get the same large databases unless you go to Oracle Cloud. So we had to rethink a lot of these patterns, right? The what we wanted to use are commodity shards, light database units, database engine agnostic, because then it opens up very many more possibilities. All of these are front-ended by HERA or OCC. HERA is the new name. Database neutral wire protocol so that we can get some database agnostic workloads. Push button automation, right? So one of the operational problems when we have many of these shards is that we cannot do the same manual process, right? So we need to get to a push button automation. And we have a later presentation where my colleagues Vincent and Deepti will talk about some of this automation, how we achieve this automation. So with this, what is our end goal? We design for survival, right? You'll see that we have this active LDR and DR loop. Our recovery time objective is in seconds, not in minutes, right? Because we talked about the availability that we needed to have. Recovery point objective is 0. We want to make sure that we don't lose any data during these cutovers or failovers, right? Autonomous disaster detection. A lot of the observability platforms that we are building is towards that. Autonomous DR triggering. How do we fail over a lot of these things automatically? And we have created procedures, automation, and so on. That's our end goal. We are getting there. We are on that journey. So we'll get there with all this autonomous databases, autonomous failovers, autonomous recovery, and autonomous operations, right? So this is a resiliency vision. So let me switch gears and talk about certain. So previously we talked about at the database level, right? But what do we do to make the data model kind of fit and work in the scenario, right? One of the key things is the keys. The choice of the keys is critical and important, right? So I want to talk about a specific key called the timed UUID, which is our PayPal specific key. So let me get into the detail right away, right? So there is something called UUID. It's a universal user ID. And if you go to Wikipedia, you can talk about, you can kind of search on this UUID. But we took this UUID and create what is called a timed UUID, which is a PayPal variant, right? So this picture here describes a 128-bit number in hexadecimal format of what a UUID is. This is the format of UUID: time low, time mid, version, time high, clock, a miscellaneous number from the clock, and then something called a node number, right? So we took this and kind of shuffled the bits, right? What did we do, really? So broke this up into its equivalent parts. This is the decimal equivalent. And we unshuffled and moved this, right? So we moved the time-based bits around. So we started with year, month, date, hour, minute, seconds, and nanoseconds, right? So the first part. So what it gave us is the same UUID. We converted this and made it a timed UUID, right? Once we have it in this format, this timed UUID is globally unique. UUID gives you that characteristic. It is decentralized, which means that you don't have any dependencies. You can easily generate this in Java. But the last one is the one that is of interest. Right? It is sortable on time because we shuffled the bits, right? These bit shift operations are very, very simple, can be achieved very easily in code. And we take this standard UUID, which is a globally unique number, and created a timed UUID of it. And so why did we do this? Because we wanted, when our data management comes in, we need to be able to generate a key that has a notion of time in it. And In the subsequent slides, I'll show how we use this. I know I've been going pretty fast, so I hope, are there any questions, Babu or anybody? Okay, so
questions, John.
Sure, thank you very much. Yeah, okay. So as I said before, the primary key, it can be used as a primary key because it is globally unique. We can use it as an idempotency key. An idempotent operation is something which we want to make sure that you don't repeat it, you do it only once. And it's a time-based partition key, right? So all of this rolled into one. So this slide is just a simple slide which says, hey, what is the possibility of collisions? Because you're generating it uniquely in each database, right? Or each session. And this shows you that there is a 50% possibility of one collision if we generate 9.1 into 10 to the power 9 UUIDs within 100 nanoseconds. That's not even possible, right? So I talked about table categories in just the previous slide. Say, okay, we take the keys and say, let's look at what these tables are, right? So we define tables as master tables and transactional tables. And in the master table, we have immutable data and mutable data, right? Two types of masters. We also have transactional data where we have to record data based on time-based recording of events, right? And this is where the time UUID comes in. Imagine if for a customer activity log, journal, payment transaction, a customer case, we can use and generate a primary key, which is both globally unique and has a notion of time. We can use that timed UUID as both the primary key and the partitioning key, right? The key sentence is that it can be used for both. Once you use that as a primary key and has a notion of time so that it can be used as a partitioning key, we can create range-based partitions very, very quickly, right, out of this key. So we will, as part of this presentation, I'll show you a data model which uses that concept. I'm just building up one by one to that final slide, right? So we talked about timed ID keys, then we talked about different types of table categories, and we can use this timed UUID as both a primary key in a master data table, which is both immutable and mutable. We can use this as a time-based range partitioning key for transactional data, which are immutable and also mutable, right? So different types of 4x4 slide. And any new table that we design, we place it in one of this. We will like to change the design of the data to fit in one of this, right? So the problem there is that sometimes this data can be hybrid. It contains both master and transactional data. And this is something that we will never mix. So we'll always kind of make changes in the application to make it fit either a master data or a transactional data. Okay. The next one is the access path. So we have created the timed ID key, we have partitioned the data. How do we manage the access? Because that is how we use the data, right? So let me start with an example. Customer activities. So we need to keep track of all the customer activities, right? So here we have an account number at a particular time, did some work which we need to record into the database as an attribute of something. And we'll see an example here, right? So these are this is a log, transaction log of all the customer activities. Now we need to be able to query this, right? Customer might say, hey, I did something on a particular day, or I don't know the day, but I did something, an activity Y. Fetch this out of the database for me. And we need to be able to do this, right? So customer need to be able to query and search the data. Now, if you were to model this, this is what we would have done, right? a customer activity table with an account number, a timed key, as I told you about the UUID, timed UUID key. This table, with this composite partition, composite primary key, we can partition on the timed key so that you will get a partition, and then you can search the specific partition, and then you can have all these attributes, right? But what is the problem here? If we were to do this, the denormalized table, and we have to query on all these different attributes, then we need to have as many indexes as there are attributes, right? Now, in a flexible system like what we have at PayPal, where we have so many different products, so many different countries, so many different the currencies that we support, this combination of the attributes could be just enormous, maybe 200 or 300 different attributes. And obviously we cannot index all of these attributes. We will never be able to index at the rate at which we need to record this, more than maybe 2 or 3 indexes at a time, right? We cannot maintain the indexes. So this model does not work. This is a traditional model. This is traditionally how we would have designed the system, right? But we had to do something different. So we came up with this denormalized index model, right? In the denormalized index model, we'll still hold the customer activity, account ID, account number, timed UUID, all the attributes, right? But we will have a denormalized index table called a CA underscore index with an account number, attribute value, attribute ID, and timed ID. Just invert the key value, right? So the account and the timed ID will go in here. Each of these individual attributes will be a row in this attribute value and attribute ID table. So we need to create an attribute ID because it says what is the number of that attribute, and then its value, right? So we know what position this is, so we know what this means, right? So keep this data model in mind because we'll see an example right away. The pseudocode will then be, so given an account, given an attribute value that we want to search, and we know the attribute ID, we run a subquery where it will scan this index table, it will fetch the account and the timed UUID, and based on that join, we can select the customer activity ID, right? If somebody wants to search on this, we don't search in the main table here. We search in the index table here, right? Using this query. And with this query, we're able to get the account and the timed UID, which forms the composite key. We come back to this and we fetch this data, right? This is a small innovation, but it had a major effect in how we dealt with this problem, right? We don't need to index anything here. Everything is here. A further optimization that we used was this CA index table was very well suitable for a IoT, Oracle IoT, or index organized table, right? When we take the index organized table and we group this around the account number, we are then able to bunch, keep together all the attribute values and attribute ID for a particular time period, all in the same block, right? This is a very narrow table, right? Obviously, IoTs perform much more efficiently if they are narrow. So with this IoT, we were able to pack a lot more. So this query was very efficient, right? And I wanted to throw our mind back to one of the tenets that we talked about, right? Optimization, cost, those things come into play when we do this. So this was an innovative way of looking at how do we re-index a very large table, the very large set of indexes, right? So this slide is from not mine, I don't use Spotify. This is from a colleague of mine, my manager actually, who is the one who came up with this scheme. And he shows an example of, he went to his activities and he searched for SPO because I wanted to search for Spotify. What am I paying for Spotify? It is able to kind of come up with this kind of type ahead information, even as we keep typing, right? Because we are able to fire off little pieces of SQL to the database to fetch this, because we are knowing like the attribute value, like this thing. From this, we can get into the details here. And from this, we will get to the details of the exact payments that were made that had the word Spotify USA, right? Now, all of this happens within milliseconds, basically because we can do this kind of queries to the database at a very highly sharded scaled system, right? Think about all the 400 or 500 million customers who want to look up their activities. We need to be able to do this millions of times, sometimes per second. And we need to operate databases at that scale to fetch this kind of information. So what did we do? We talked about keys. We talked about data model. We talked about partitioning. We talked about creating an inverted index. And this is how it looks. This is the scaling out part, right? So we started out with a single database in this, but we found that we ran out of capacity there. We needed to scale this out. So how did we scale and how did we shard? For sharding, we needed to identify a shard key. So we took the account number, which is an excellent key to shard on. We created a mod of that, the account number, to 128. So that gave us 128 buckets. And we took that and sharded it out this way, right? So bucket S0 to S127, this is shard. And then we have this horizontal way of looking at this, and then the vertical way, which is a time-based, timed UUID way of looking at this data, right? And this is how we could do this and satisfy both the requirements of being able to scale and with sharding, and also create this time-based partitioning so that we can scan and show the right data from this system, right? It's a combination of this. It's a culmination of how we think about data, how we design data, how we use all the various characteristics of the Oracle database, including IoTs and so on and so forth, right? So currently this system has 8 physical shards, about 100 terabytes per shard, and billions of reads, writes by day and table. So this kind of is like a summary of building up the story to this point of how did we do this. So let me pause here and see if there are any questions or comments. Okay, I think sure that it looks like there's just a comment here. So anyway, kind of this is my final slide. So we went through a lot of experimentation, right, to get to this point. And you will see that the design that I just described now is a database engine agnostic design, except although, well, we use Oracle IoTs for optimization, but we could take that and use that in any other relational database, right? Now, the design solution has many characteristics of NoSQL, right? And this slide shows you 3 characteristics that we used. Couchbase, which is a NoSQL, is a key value store. It can also be used as a document store. The attribute table that I described fits here, right? It's a key value store which is indexed by the account ID. We solve this problem, right? Partition key. This is Cassandra. In Cassandra, the partition key is, we can create a timed ID based key, which Cassandra supports, to provide this time range based queries, right? We took that idea from there, or rather we adopted the idea from there, right? A document database and a time based store. Finally, Elasticsearch, which gives you the ability to search. And I showed you a slide as to how we can search and what are the queries behind that. We map that to the solution, right? So NoSQL gives you flexibility, scalability, and performance, but it doesn't give you ACID. It doesn't give you a lot of other things. But what we have shown here was that we can take the principles of NoSQL, key value, timed UUID, and a lot of that, put that together and come up with our own solution to solve our problems, right? So the key point that I wanted to make here is that, yes, innovation is at PayPal is the one that sustains us, enables us to carry this $1 trillion business. So sometimes, as the saying goes, necessity is the mother of invention. So we have to continually keep innovating, and as I said before, you'll see that the other presentations that my colleagues are going to give you will give you further insight into how we do this at PayPal. So with this, I think we have 3 minutes left in the presentation. I hope this was of some insight to you as to how to think using the traditional database to solve high-scale problems, and that if we put our minds to it, we can come up with the right solution to pretty much any problem in terms of data. So with that, let me close. Thank you all once again.
John,
Yep.
one quick question. Are all the
Sure.
shards in the same data center or same region?
Yes, all of these shards are in the same data center. But if you go back to this slide that I have, let's see. This is our vision here, right? This active shard, this is the active shards, right? All the red ones are the active shards. We have what is called the local DR, right? They are in the same data center.
And you're not sharing.
You're not sharing.
I'm sorry. Are you guys able to see the screen?
Yes, John,
Yes.
go ahead.
Okay. Okay. I was showing you this screen, right? We have the active. There are two data centers here. One separated by this thin blue line, right? So this is the live data center. This is the disaster recovery data center. We have the active database. We have the LDR for shard 0. We have the DR here. So there are 3 shards here. Although it is sharded, we're all in the same data center. But if there is a failure of any of these, it can go to either the local DR or the remote DR. Does that answer your question? I hope it does.
Yeah, thank you.
Okay. Any other questions?
There's a question on how the index table is being inserted into.
It is this slide problem. This slide problem. Okay, that's a good question. So we do need to duplicate the data, if that is the question, right? So when we insert this customer activity table, the pieces of the code will kind of say, hey, this is an attribute. What is the attribute ID? We have some metadata that says this column number is this attribute ID. We will insert both this table, customer activity table, as well as the inverted index table in the same transaction. right? So if you think about it, this is Oracle, and we can get this multi-table transaction ACID capability, which is not available in NoSQL, right? In NoSQL, we could have had a problem here. We could do the same thing in NoSQL, but we won't be able to create the rigid ACID properties. So that is how we do. So both these tables are inserted in the same transaction.
Yeah, you have separate
answers
insert statements from the applications doing that.
That is correct. But there is
Yeah.
one commit statement. Yes.
Just out of curiosity, would a row trigger not be suitable also? Playing devil's advocate.
Yeah, a row trigger would suit. Could have achieved the same same functionality, but when you place a row trigger, the CPU requirements shifts from the application to the database, right? When we talk about scaling, we want to make sure that the database does the least amount of work for what it's supposed to do, because scaling the database is difficult. We can scale the stateless systems by adding more JVMs. We can continue to scale out on the application side easily, as long as we are able to maintain the number of connections that are required, right? So the philosophy at PayPal is that we will try and use the capabilities of the database to its extent, but not more than what is required. And one of the reasons also is that the moment you put code in the database with a PL SQL or with the triggers, it's a 0 or 1 story, right? I talked about the need for these systems to continually evolve. So as they evolve, if you have a trigger which needs to change, either the trigger is on or the trigger is off, right? So when we make a change to the trigger, we need to, that causes invalidation. That will bring down the system. First of all, you'll not get a lock to change the trigger, DDL lock, right? So that is a no-no in our high scale environment.
Okay, one small follow-up question. Do you then do you do two inserts, one for the left table, one for the right table?
That is correct.
Or do you have multiple inserts for the right table, one for each attribute?
No, it depends on how the clients call the API. If the API comes in here with all the attribute information that is required, we will insert as much attributes, right? So these attribute columns are not null allowed columns. So we can have a very sparse set of attributes because think about it here, right? So there is a set of activity that happens at a particular time. The account number will be the same, but the time UUID might be different for different attribute values, right? So this can be a very sparse table. This will not be a sparse table.
Okay, thanks.
Sure. With that, I think we are out of time. So we have 12 minutes until the next session. Again, thank you all for listening to me. I know I compressed a lot of information into this, but I hope you came away with a sense of the scale, innovation, and all the other things that we do at PayPal. And thank you for being very, if you're a PayPal customer, thank you for that. Thank you for placing your trust in us.